So we want to prove this theorem, Riemann-Roch theorem, which says that for any divisor, it will give you this equality. The difference of L d with degree of d plus 1 minus genus is exactly equal to this some other L of some other divisor. Key thing is that this theorem is saying that there is a magical divisor W such that W minus d is what you are getting. So this W will be called a canonical divisor in the divisor class group. So there is no reason why this thing should exist. So for that we go via this new object called ADEL. So which is just defined as a tuple of infinitely many rational functions. Yeah, so instead of a single rational function, now we are looking at kind of function field raised to infinity, all kinds of tuples, and we can define everything that we did with functions. So we can define valuation with respect to a point, we can define addition, multiplication, and hence we can also define the LD sheaf idea, and now this is called AD, where A is an ADEL, A is the ADEL. And we can look at, so this again will be a vector space, and we can talk about its dimension, which turns out to be infinity. So this by itself is not very useful. So what will be useful is the dual of this, which is A modulo AD. Okay, this will turn out to be a finite vector space, and that, so we want to now show that. So before that we had said that every ADEL R has an associated divisor, which is kind of this infinity that we had for functions, the poles, such that R is in the ED sheaf. Basically, it's R plus dr should be greater than or equal to 0. So you should be looking at dr as the poles. Yeah, so think of dr as infinity. So if R was, instead of an ADEL, if it was a rational function. I think you weren't there for the ADEL class. Yeah, do you want a? Okay. So if R was a rational function, then you just look at the poles, and that gives you dr. So it was, we called it R infinity. Same thing you can do for ADELs also. That is the associated divisor dr. It will be positive. Key thing you want is it should be positives, and R should be in ADR. Second property which we have shown is that the dimension is actually degree difference. Dimension of the quotient is degree difference. So this is much better than LD prime over LD, because there you only got an upper bound. And third is the most important property, which is that AD and A, of course, these are infinite dimensional vector spaces, but their quotient is finite, and it's exactly equal to the degree of speciality. Right? So this is, recall that this is equal to LD minus DD plus 1 minus G. Right? So for every divisor, this thing will be true. That is what we are saying. Okay, so let's go to the proof of third property. We had started this. So first we show that the dimension of this quotient vector space is at most delta D. How did we show that? Well, I don't think we have shown it. So we are in the middle of the proof. So take a basis R1 to RH of A mod AD plus K, and this is H is the maximum possible integer. So by the first property, you have these associated divisors dr1 to drh, Ri is in 8 dri. Take the LCM of this, which basically means that these are divisors, right? So you have, for every point there is a order. You just pick the maximum and define d prime. So now every Ri is also present in AD prime. So you have this common divisor d prime now associated. This continues to be a basis of AD prime mod AD, okay, because it was a basis of the bigger thing, so of course it's a basis of the smaller thing also, and it's there, it's present in AD prime plus K. So we will just do some vector space calculations, some dimension arguments. It is nothing to do with complicated algebra. So here we will just look at AD prime plus K mod AD plus K is isomorphic to AD prime modulo this subspace. So what is this? This is just a, basically you take a basis of AD plus K, AD plus big K, take a small k basis, and similarly you can take a basis of AD prime plus big K. The two, there might be basis elements which are common. So the common part is the intersection. Okay, so you are removing them. So if you remove the common part, what remains is the difference. So by that you can show this in general for vector spaces.
Why are we studying the AD plus K? Why not A mod AD kind of thing?
Oh, A mod AD is again infinite. That is the problem, yeah. You can study A, you can study AD, and you can study A mod AD, but you will still not get close to delta D because they are all infinite.
Don't you have to show that this was finite to show that the HL is the maximal?
Yeah. So
There could be infinite basis.
no. So for example, you can just, yeah, there could be an infinite basis. So why don't you just take H to be delta D plus 1?
I have written in the first statement that pick the maximum as per.
Yeah, but maximum can be maybe once we finish this proof, you will see that it won't matter. It will be correct. So let me give this proof. It's a very simple proof. Then you can come back and say that take H to be either the maximum, or if it is infinite, then you take it to be delta D plus 1, say. So maybe I can just write here maximum H less than equal to delta D plus 1. Okay, so this can be the definition of H. Maximum you can go up to delta D plus 1, and we will show that actually you cannot. You can only go up to delta D. So you will show two things at once. You will show that basis is finite, dimension is finite, and delta D is an upper bound. This proof will prove the two things simultaneously. So let's continue with this right hand side. So this is isomorphic to, or maybe I should copy that. So AD prime mod yeah, so we are here. Now what is this? This is AD prime mod LD prime plus AD. Why is that? Well, so in both these objects, so AD is clearly contained in AD prime, so AD is common. Beyond AD, you only have rational functions in big K, right? So what are the things which are functions and present in AD prime? That is by definition LD prime. Fine. So from here, from K you get LD prime.
Shouldn't this thing be the reciprocal? But go to the formula that you have written in the last page. U plus V by U is V by V intersection, right?
Yes. It's basically U is already present in both numerator and denominator, so U is kind of 0. So you have to use V modulo something, but something should be what? It should be essentially the elements of V which are already present in U, because they are to be killed. So this is true also for infinite dimensional vector spaces. It's a completely qualitative property. You can just think of this proof as a construction of basis and then finishing the argument. It doesn't require finite dimensional. Yeah, so now we are reaching, now we have introduced L sheaf, and we'll just keep doing this, keep improving on this. So AD prime mod LD prime gives you what? So basically we want to reach property 2, right? Property 2 is something that we know exactly. So we want to reach AD prime mod AD. That's the goal in this calculation. So let us just jump to that. So AD prime mod AD mod LD prime plus AD mod AD. Okay, now in this quotient we can you see that AD is present in the numerator and in the denominator, so we can take mod both sides and the quotient will not change, it's isomorphic, and which is isomorphic to this thing mod. Here again you can do that trick, so L intersection trick. Right? This is clear. In the modulus, you can again do LD prime mod intersection with AD, and yeah, so now you are looking at functions in LD prime which are of the type AD, which is, so you are not looking at ADL, you are actually looking at functions which are greater than equal to, I mean, plus D prime and plus D both is greater than equal to 0. Which basically means that this is just LD. Right, and this is something which we now understand better than what the thing that we started with. So from here now you can deduce that the dimension is equal to degree D prime minus degree D minus LD prime minus LD, right? We know all the I mean, we know the first quotient and we know LD prime and we know LD. So we get this by property 2 and properties of LD sheaf. And yeah, now we can turn to genus. So this is equal to LD minus DD minus LD prime minus degree D prime, and so I don't change the first thing, and the second one I can say LD prime minus DD prime is the bottom threshold is, lower bound is 1 minus G. So we can put that here, right, and this is the degree of speciality of D by definition. Is there a mistake in this? I think I made a mistake in this comment. It's not 1 minus G, G minus 1. Yeah, so LD minus DD plus G minus 1. So that's the degree of speciality by definition. So you have an upper bound. So you have shown that A mod AD plus K is less than or equal to delta D. I mean, this implies that H is less than or equal to delta D, which implies this, right? So, I mean, your question was that what happens in the infinite case? So in the infinite case, you can go up to delta D plus 1, H will be that, and then you will do this argument, but this argument will actually say that H cannot be delta D plus 1. You will get a contradiction. So H has to be finite, and then this also tells you that H has to be delta D or less. So it's fine with also maximum with the infinite dimensional case. Yeah, so we have this first time we have identified an Adel object which is finite dimensional. Okay, so this is a fundamental construction.
And this is a proof. We are finding genus, right? For any basis, just find the LCM. You prove the equality, then LD prime and DD prime has to be equal to 1 minus G.
Yeah, so for such a D, the degree of speciality will be 0. Delta D will be 0.
Find D prime from the basis, right? So we can always find 1 minus G that way also.
D prime from, yeah. Yes, so, but it's not clear how you will do this in an algorithm, because these Adels are infinite objects. So it's not clear this, how do you work with infinity? A is infinite, AD is infinite. Yeah, so this is, in the algorithm you have to analyze more, which I have not done. But you are correct that, in the end, after I have proved more properties, this will give you far more than just genus. You can actually compute, you will actually be able to compute this thing that Riemann-Roch says, the canonical divisor W. So for the computation of that, which is basically related to A mod AD plus K, that object you will be able to compute. Yeah, but that's jumping far ahead. So we have to, right now we actually have to prove now equality with delta D. So let's first do that. that the dimension of this dual object is at least delta D. So this object is clearly a dual, right? LD was the primary object that we had studied, and this is kind of A modulo LD. So it's a dual thing, and we want to show that it's actually an equality. So all we have to show is that it's at least delta D. This will be actually much easier to show. So you know that by Riemann's theorem, there exists a D0 such that L D0 minus degree exactly equals 1 minus G. So consider the LCM of D and this D0. Right, so there is a D0 which is given by Riemann. You don't know what it is, but you know that it exists, because the place where it meets the threshold, that is called the genus. That is what we call 1 minus G. So by definition D0 exists. By definition of genus, D0 exists. So if you take the LCM with the input divisor, which was D, you will get a bigger divisor, right? And the bigger divisor will again satisfy the equality. So LD minus DD is also equal to 1 minus G, because we have this basic property from LD sheaf that when you increase the divisor, the difference reduces, but it cannot reduce below 1 minus G, so it will remain 1 minus G. And so now let us look at the previous calculation, which is ED prime plus K mod AD plus K. We had shown that this is the same dimension as the dimension you are interested in, E mod AD plus K. No, sorry, it's not the same, this is something else. But anyways, I can calculate this dimension. This dimension is this, which is sorry, this was D prime. D prime is the bigger one, and which gives me what? No, we have to use this formula that we showed. Yeah, let's do it in steps, jumping too fast. So what we had shown is that this equals degree of, I mean, in the end we got this L minus D of big D and L minus D minus L minus D of D prime. So let's continue using that. So first for D, then for D prime. Yeah, that is what we had proved. We had proved it for any D prime actually. Any D prime greater than or equal to D. So we are using that part of the proof, and we know that LD prime minus DD prime is 1 minus G. So this is then equal to delta D, because it's LD minus DD minus of 1 minus G. So that's the degree of speciality, which is the lower bound, right? Which gives a lower bound for A mod AD plus K. So A mod AD plus K is clearly a subspace which is at least as big as the one above. So it has dimension greater than or equal to delta D. And the two together mean that this is equal to delta D. Is that clear? Yeah, so this is really a consequence of what you saw in Riemann's theorem, and correcting the LD sheaf to AD sheaf gives you equalities. So you use that, use genus as the threshold, and the proof is not very difficult with all those tools. Okay, so so this A mod AD plus K is a good dual of LD. Okay, because it tells you about the remaining part, which was the degree of speciality of the divisor, and so LD we were calling the L sheaf, LD sheaf. Similarly, this new object is also you can also call it a sheaf. It's the A mod AD plus K sheaf. So it gives a new sheaf. I mean, we haven't defined what a sheaf is, but it's a vector space that you have now defined, and it's a dual of the first vector space we had defined. Okay, so we'll use this to now prove Riemann-Roch theorem, but we have to finish that proof. What we will do is now we look at the maps, linear maps from this new sheaf to base field small k. So we look at the home from this to homomorphisms from this to small k. So that will be the beginning of differentials.
So what did you say? What were we trying to do? We are trying to construct homomorphism from AD by AD plus K to K.
Yeah, so we'll now study this object A mod AD plus K via its homomorphisms. The K vector space A mod AD plus K, because this is finite dimensional, via its dual. And what is the dual of a vector space? Yeah, so this kind of, we are using dual also in two ways. First, we said that we want to have a dual of LD sheaf, which is this A mod AD plus K, and now we'll study it. We want to study this, so we'll study this via it's vector space dual, which is basically homomorphisms that send elements from here to the base field small k. So that we define as a differential of the function field. So a differential of the function field k, or equivalently of a curve, is a map omega that sends this object to base field small k. For some divisor d. Okay, so for a function field we can define differentials. These are basically maps which these are linear maps over the base field small k. They send this A mod AD plus k, big K, these functions are mapped to field values, base field values. These adels, in fact, yeah, it maps the adels actually into the base field in a linear way. Yeah, this may be conflicting in your minds with the notion of differential as in derivatives, right? How is this related to derivative? So for that you have to recall that a differential in the sense of derivative, for example dx or dy, those things are also seen as linear maps on the tangent space, right? So tangent space is also kind of a basic sheaf. So it's a similar idea, but here it's much more algebraic and generalized. So we have actually gone from functions to adels, and now at the level of adels we are talking about linear maps. So basically you have to associate adels with tangent spaces and linear maps on adels as differentials.
So is this adel actually the algebraic analog of tangent spaces? No.
So adel is kind of roughly like a tangent space. Then in that vocabulary or in that dictionary, here you have the differentials. Like dx and dy. That is what now we have defined as differential of k. Okay, so these are the more complicated things. So this is why the name differential is not out of place, but of course in the course when we say differential we will mean this, we will not mean the usual engineering dx or dy or d of x square. So differentials are these objects which satisfy these identities, right? D of x square is equal to 2x dx, right? So these are differentials. I mean the key property of differential, Leibniz rule. But in like even to begin with a differential, what you want is you want some linear map on a vector space. So that vector space in our case is this adel thing, and we are looking at homomorphisms of it to the base field. Right, so this must have been the motivation to define it in the times of Roch. And what good is this for? So that you will see very soon. So we'll denote it like this. So omega of big, So we'll actually skip the subscript. Let's just call this omega d. So this is the home. Okay, so big omega d is for a divisor, are these linear transformations from Adel quotient to the base field. This is a set of differentials, and now we'll study properties of this. So the first property is what can you say about omega d prime and omega d? What is the relationship between them if d prime is a divisor, at least divisor d? So one thing to remember, I mean, which will help in all our future properties, is that you are interested in homomorphisms or maps which have to annihilate AD plus K, right? Because you have this mod AD plus K, so maybe this should be remembered. So any omega here has to annihilate the modulus which is AD plus K. So you are interested in those linear maps on Adels that have to annihilate all the functions, and they also have to annihilate all the Adels which are greater than or equal to minus d, right? That is what essentially you want. So if an Adel is annihilating d prime, it's, I mean, AD prime, it's clearly also annihilating AD. So which means that this is a subset, right? So when you increase the divisor, you go to a subset. So it's the opposite direction. So set of all differentials of K is denoted by just omega, and if you want we can put the subscript here, K, big K mod small k, which is the union of all these. Okay, so if you go over all the divisors in the in diff C, right? So big function field of transcendence degree 1 big K over a base field small k defines a smooth projective curve, that's Ck. Go over all the divisors, look at all these differentials, that is the big omega set of all differentials. So that is going to be a very useful object, as you will soon see. So the first property is that omega is a big K vector space. Clearly it's a small k vector space because these are linear maps over small k, so you add two things, you get a third differential, but over the function field also it's a vector space, and in fact it's a rank 1 vector space. Okay, so all the set of all differentials actually is rank 1 over the function field. that's a surprising fact. Although you could have predicted it by the dictionary we had between the engineering differentials and these Adel based differentials, because in engineering differential, if you remember, you have this so if y square is equal to x cube, it means that 2y dy is equal to 3x square dx, right. So you can see that there are two differentials dy and dx, but they are dependent, because one you can multiply by a function and get the second one, right. So because those engineering differentials are dependent, you could have predicted that these abstract differentials are also dependent. There is only one which is needed, but the proof is not so easy. Proof has to be more abstract at the level of Adels, because this is a different object. So let's do it. Yeah, first of all, why is it a big K vector space? So you have to define what happens when you multiply by a function. So omega is a differential and x is a function. So define x times omega to be so what do you want to do? You want to map Adels to the base field, and you are given omega, right, which is an element of Adel. I mean, it's a map from Adels to constants. What should you do with x to define x times omega? Well, the natural thing, so omega, when you apply it on an Adel, you first multiply the Adel with x and then apply omega. So an Adel R, you first multiply R with x. This you can do because a function is also an Adel. Adels can be multiplied, so Rx is that Adel, and then you apply omega. Right, so that's the obvious thing you should do. That gives you another differential, right? From omega you can get x omega. Okay. So you know how to multiply by functions. Now you have to also show. Actually, two things can always be added. So that I think is easy. Oh no, there is one thing. So this big omega is all the differentials. So they may be for different divisors. So let's also check that. So pick another omega prime which is coming from omega d prime. So omega is in big omega d and omega prime is in big omega d prime, and these d and d prime are independent. So now what is the way to add them? This also we have to specify and show that it is again a differential. So for that we use the usual trick. We consider a bigger divisor E, which is LCM of d and d prime, which means that E is at least d and it is at least d prime. Right. So, pick a bigger one and then what is omega plus omega prime? So, omega plus omega prime, I will see it as a map in ADEL, this. So, what it does is that it on R, it just goes to omega R plus omega prime R. Well, clearly omega or omega prime are field element are constants, you can add them. So, this is a linear map, but you have to check whether omega plus omega prime is annihilating AE, that you have to check. So, what is omega on AE plus K? See, yeah, so why don't we write that first? Or maybe the claim is that this is 0. Why is it 0? Because AE plus K is this is true, right? Function ADELS plus E greater than or equal to 0 implies that yeah, correct, okay. And same thing with omega prime. Yes, omega and omega prime, in other words, are actually differentials over this of omega E. They are differentials in omega E, and you can add them, and you will get another differential in omega E. And hence, you can add any two differentials. That's all. Right, so I have shown you how to multiply a differential with a function, and I have shown you how to add arbitrary differentials over different divisors. So that's a big K vector space. Now comes this abstraction of the engineering fact that for a curve the differentials are actually, there is only one. There is only one generator. I think I have something I have messed up. It should not be like this. E should be less than equal to D. Should be opposite. Should be GCD. What was the property for ADEL comparison? Yeah, let's check that proposition. I think I am using it opposite. Yeah, when the divisor is bigger, AD prime is bigger. Sure, that was the degree. Yeah, so it's opposite. So actually, now it's correct. So since E is less than equal to D, AE is actually a subspace of AD. You have to take GCD. Yeah, you have to go smaller. There omega plus omega prime lives, and So, it will be good to remember that. So, we can remember two things from this proof. First is that when you add something in omega d prime, where you go is GCD. So, sum of two different divisor based differentials is actually contained in the GCD. That is what we saw. And for a function x, when you multiply with differential, where you go is x plus d. Okay, this is the setting of the proof. X was a function, omega was in omega d, small omega was in big omega d. Then where is x times omega? It is here. This was in the previous proof, first property. Because we did this r times x, so you can recover from there. Yeah, okay. Any questions? Not sure about the second property. How do you show this? So, let us say omega annihilates, well, omega we know annihilates AD plus K. So, what does x omega annihilate? X omega annihilates functions which are here. And where is x times AD? So, a function f plus d is greater than or equal to 0, then xf is where? This implies that xr plus d minus x is greater than or equal to 0, isn't it? Yeah, so I think it was a mistake. So, it should be d minus x, not d plus x. Because these functions x are, I mean these adels are greater than or equal to x minus d. So, you have to use d minus x here. Fine. These are typos from earlier lecture notes. Okay, so this will be now important in the next part of the proof, which is dimension 1. Let's start that. So, let us pick two differentials. from two different, two arbitrary divisors, d prime. In omega big K over small k. We want to show that they are related, one is a multiple of the other by a function. That's a very powerful claim we are making. So how will you show it? So it's not as easy as the engineering proof, where you just looked at the equation of the curve and applied the differential or differentiated the bivariate polynomial.
Over here we have to use the GCD concept, right? D and D by GCD.
Not just that, you have to use arrows. You basically have to construct these maps. It has to be a more abstract proof. So what we will do is, let's pick a positive divisor E. The thing with positive divisors is that LE is what is the L dimension of a positive divisor? Is bounded by the degree. Right? I think this is also not very important probably to see. But yeah, anyways, this for a positive divisor, the L you can see is at most the degree plus 1. And now the abstract proof will be so consider two K linear maps so one from LD plus E and the other from D prime plus E. So this map is how do you map a function to a differential? So you are given omega, right? You have to use omega. So basically that function you should just multiply with omega. That's the plan. And here just multiply function with omega prime. X prime goes to x prime omega prime. Let's check whether this makes sense. If I take an x in LD plus C and multiply by omega, which was in omega d, what happens? Where do you end up? X omega is a new differential, and Yeah. So d minus, the previous thing we had was d minus x, right? When you multiply by x, then you get to d minus x, omega d minus x. So that will be d minus e. So you get to minus e. And same thing with the second one. So you are getting this because d minus d plus e. Yeah, so you can map functions to this differential. We are doing this because we want to compare omega with omega prime up to functions. So xx prime will help. This map, this picture will help. So first property is that I and I prime are injective. Why? Well, what will happen if x omega is equal to 0, the 0 map? See, if x omega goes to the 0 map, so on every adel, it is annihilating every adel, then it means that omega itself must have been annihilating every adel. Right? Because x is just a function, so x omega equal to 0 implies that it's 0 on every adel. Actually, on every adel, it is mapping it to AD plus K. A minus E plus K. Because that's the concept of 0 in omega minus E. So, yeah, I think that was correct. Sorry. X omega no, wait. Yeah, A minus E plus K, it anyways has to vanish, and it anyways has to annihilate, and actually it's annihilating now everything. So it's annihilating all the adels, right? X omega is a transformation annihilating every adel, which means that for every adel, you are saying that x omega on R is 0. Which is basically saying that omega on every Rx is 0. But I mean, if you multiply an adel by x, this is a kind of a it's an automorphism of adels. Right? So it actually means that omega R is 0. When you want to show that omega R prime is 0, you just use here R to be R prime over X. R prime over X is also an adel. So from the first property, you get the second property. So these two are equivalent properties. So which means that omega is 0. Right? So you have these equivalences. So which means that these two are injective maps. Uh, okay. Right. So, but how will this help? So, injective is almost a trivial result. Uh, Basically, you have an embedding of L d plus E in omega minus E, and you also have an embedding of L d prime plus E in omega minus E. You have some information about their dimensions. So, let us compare. Suppose you can show that these two embeddings, they overlap, they are not disjoint, right. So, if they overlap, then it means that x omega is equal to x prime omega prime for some x and x prime, which will finish the proof. So, we just have to show that these two embeddings, the range is too small, so these two embeddings actually overlap. They overlap in omega minus E, and then we will be done, because that will give us x and x prime such that omega x omega is equal to x prime omega prime. Is that clear? So, let us check that by looking at the dimension of the image of I and the dimension of the image of I prime. So, this is equal to image of I is just the L d plus E, image of I prime is just L d prime plus E. So, we have good information about these two. So, let us write that. So, this is greater than equal to right. This is by Riemann's theorem. L cannot be too small. I mean, L minus D cannot be too small. It is given by genus. So, these are the lower bounds. Now, degree is very well behaved. It is just you can sum these things up. So, you get degree of twice the degree of E plus degree of D plus D prime plus twice of 1 minus G. So, it is here that I will make E bigger. I will make it so big that this quantity is at least this. Right, I am allowed to do this because big D and big D prime are fixed divisors. We fixed them in the proof. E is free, so I can just pick a very big positive divisor, so that DE compensates for this negative contributions of 2 1 minus G, and the whole sum is at least degree of E plus G minus 1. Okay, and what is that? So, this is equal to L of minus E minus D of minus E plus G minus 1. Why is that? Essentially, I've added only L of minus E, right? I'm claiming that it's 0. Why is that 0? Well, E was a positive divisor, so you basically are saying that functions which are greater than equal to E, so there should be no poles and there has to be a 0. Yeah, but there is no such function which has no poles but has a 0, except, so only functions will actually satisfy. There is no non-constant function. Yeah, I think this is the important thing. It's not this LE business. It's actually L minus E that I want. This is what I wanted in the end. So positive is important for that purpose. So it gives me this in the end this L minus D plus G minus 1. So that's delta minus E. And by a major proposition, delta minus E happens to be the omega E, dimension of omega E. Maybe one step I write, because this is this we know by proposition is the dimension of A mod minus E plus K. Now, when you look at the homomorphisms of this to constants, you will get as many as the dimension of this. So that means it's also the dimension of omega minus E. Right. So what have we shown? We have shown that the two images sum up to more than the dimension of the range. So we are done. Right. This actually means that the images overlap. It's not 0. They can't be disjoint. They cannot just have 0 as common. They have to have something more, because their sum of the dimension is bigger than the range. So you pick. So this means that there exists XX prime such that image of omega, image of x and image of x prime are equal, and that means nothing but that the dimension of omega over the function field is 1. Okay, so it's a cyclic vector space, rank 1. So note that we used two kinds of dimensions here. We used dimension over constant field. We also used dimension over. Using that, we got the dimension over the function field. And yeah, so this is obviously a far more abstract proof than what we were used to in engineering by just differentiating, right? So this is the proof by arrows. which can be generalized to even more abstract levels. For example, in cohomology theories. Okay. So yeah, once we have shown that it's rank 1, dimension of omega is 1, you can talk about a unique differential, right? And that unique differential, in the next class I will say that look for the unique differential, look at the associated divisor, and that is the canonical divisor. And that will finish the proof of Riemann-Roch. So now we are very close to the end of Riemann-Roch. So pick and consider its associated divisor d omega. That's what we will call W. Right, so we'll formally define this next time. It will need some more care. Because the thing is that it's not unique, right? You can pick a generator multiplied by a function x, so x times omega. That can give you a different associated divisor. So there are actually infinitely many ways to get this associated divisor d omega. Neither omega nor W are unique. There are infinite possibilities. So I have to give a proposition that although there are infinitely many ways, they are somehow all equivalent. So I have to then I can say that okay, canonical divisor is a unique object. So once we do that, we'll just prove Riemann-Roch using this L of W minus D. W is a unique divisor. Of course, it will know about genus, but it will know much more. It's a very special thing. It knows almost everything about the curve and the function field.
So these spaces A by AD plus K, can this be explicitly constructed? Can one provide a basis for it?
Yeah, that is what Rishabh was also asking. See, the thing is, once I have defined this canonical divisor, I think from that point on I can give an algorithm. So some more work is needed.
So canonical divisor is more explicit. We will use that in order to.
It has many nice properties. Yeah, once you know that it exists and how it exists, then you can use it to.
I was thinking of the opposite direction. If you can construct A by AD plus K, then.
No, but that is infinite. A is just an infinite tuple of functions. Functions themselves were infinite. And now this A mod AD plus K, you are not just looking at A mod AD plus K, right? You are looking at linear maps from these two constants, which is like, it's very complicated because the way we have defined this omega D, the two quotients, the two things which appear in the quotient, they are infinite dimensional. And from there now you are looking at these matrices. This home is actually not matrix, sorry, it's a vector. You are taking a vector inner product with the adel to get a constant. So you are looking at vectors over adels. So adels were bad enough. Now you are looking at vectors over adels, which is even worse. Yeah, so right now it's not clear how will you make this into an algorithm. But very soon it will become an algorithm because of the canonical divisor that you will get. Essentially these, although omega d's are such big, there are so many omegas, still ultimately they come from a unique one. So instead of working with these things, I will just try to compute the unique one. And that will know about all of this machinery.